Today on ONNX, we're going to be working with Seth Juarez to find out magic numbers using machine learning. Check it out. Welcome to another episode of ONNX. This is actually our first show that we're shooting in 2019.
What?
Yeah, and so we've got Seth Juarez, who's going to be telling us about machine learning and PyTorch and stuff like that.
Yes, but mostly .NET.
But mostly .NET. So I actually think this is a little bit weird. I'm interviewing you.
Why?
Yeah, because well, you're like the pro interviewer here at Microsoft.
Who's this guy? I mean, you know what I'm saying?
Yeah, so I'm gonna try my best today.
Okay, and if you disappoint me, you know we were gonna have that thing that I said.
Yeah, okay, for sure. So, what is our topic?
Okay, so today we're talking about the ONNX Runtime and how to use it inside of .NET. And for many of you, this might be a little confusing, right? But when it comes to machine learning, the cool thing about it is that there are two phases when you're doing machine learning, specifically with deep learning, which we're going to talk about. The first phase is a data scientist or a programmer, or even you, because I think anyone can do this, is you train a thing called a model. And you need to think of a model as a function or an asset or a jar file or an assembly or whatever. It's something you call. And so once you train that model, the question becomes, well, now that it's done training, how do I actually use it?
Totally.
And so that's what we're going to be focused on today, hopefully. I'll get a little into the training if you have any questions. I'd love to answer any questions about how these things are trained and what it's doing. But once you have that model file, all you got to think about is bring the file into my project, put some stuff in, get the answer out.
Right. So it's a little bit like a gymnast trains for 4 years, does all of these contortions, and then somehow they go to a different city where the Olympics are being held, and they actually basically do their model and they end up with a gold medal.
Yeah, one thing.
Yeah.
You're absolutely right. There is a lot of contortions.
Yeah.
That's basically all of machine learning. Literally the secret here. But yeah, but it's a little bit different in the sense that imagine you have so let me see if I can come up. Imagine you've set together your sprinkler system, and for those that don't know, we have automatic sprinkler systems in some part of this country, and you turn it on and then water goes through the pipes. But imagine being able to turn off and off valves so that you can water all of your lawn at one time, the best way possible.
Right.
So what happens is a model is basically like the pipes. Where you turn the knobs is basically what we're doing. We're trying out a bunch of settings in the knobs so that we can cover all of the things in this case. In this case, we're going to recognize numbers, digits. Okay. And so so you can see here, if we can go to my screen, basically this is just PyTorch. And you can get this is a GitHub repo. We'll put a link on it. It's just deep learning with PyTorch under my GitHub account, which is Seth Juarez. Basically, these are the pipes I set up. I set up this thing called a convolutional neural network. These are the pipes. And then what we do is on the interior, there's basically a bunch of numbers that when another digit that we drew comes in, we multiply, we pass down, we do some things, we multiply, pass down. We need to find what those numbers are. And as you can see right now, that's basically what it's doing, because I ran it before we started. And you can see that it's just going through and trying to figure out what are the best numbers to multiply this digit we drew by in order to get the answer right out. And this can take a while. There's some models that I've run before that have taken days. Some take weeks. But basically, once you're done with the training, you have this file with a bunch of numbers.
Right. So you have to say, hey, boss, I can't do any work for the next 2 weeks. I'm training this model.
Or you could use our cloud.
Yeah.
We rent by the hour, I believe. I think that's what
something like that.
Yeah.
So we actually should give a pitch to VS Code.
Yeah.
So is VS Code a good IDE or editor for Python?
Absolutely. I absolutely love it. And the reason why is not just because Python is sort of built in and I can do some crazy things like, for example, what's this module thing? I can actually go to the definition, and in Python, it will bring it up, right? Like not just like here's where the assembly is, because but it's literally this is the code. And so a lot of the times when I'm looking at how this stuff actually works, I can go and see exactly how it works.
Right. So you can understand.
Yeah, absolutely. But again, this is Python stuff, and it may not be interesting to you as a .NET dev. The only thing I wanted to point out is that we have this loop right here, and you can see this loop here going throughout, is that we go through all of it. So we have 60,000 hand-drawn digits that are
Okay.
28 pixels by 28 pixels,
So this
grayscale.
this is your test data.
This is the data we use to train.
Yeah.
And so what we do is we give this thing all of this test data. It's like the water going through the pipes. And this loop right now is going through and adjusting all the knobs.
Right, trying them in different ways.
Yeah, and once it's figured out the best way to do it, imagine pulling that out of the dirt with the knobs intact, and then we're going to put it somewhere and just turn the water on.
Right.
And that's what we're doing. And so here, right now, I'm running through, this takes about 15 epochs, but it's already about 98% accuracy.
Right.
But basically, the output that you get right here, let me go to Reveal in Explorer, is this thing called model.ONNX. And if you zoom in, this is a really cool, this is called Netron. It's a really cool program for looking at neural networks. You can see that their input is this thing that they labeled 0. And then it basically goes through the W, what the size of it, and that's just a bunch of numbers. The B so we multiply and add with this, we add this on, then we make it smaller, then we run a function, then we do this all the way till you get an output that's of size 10. You can see that 1 by 10 here. And basically, we want to see if the digits between 0 and 9, and so there's 10. And so in the 0th index, if you get a 1 there, that means that pick 0. If it's not sure, you just pick the max index, and that's the right answer.
Right, and the reason that there's 10 of these elements is because we're only, all of these images only go from 0 to 9.
That's right.
Right, so if the images were 0 to 99, then we would actually have 100 elements to choose from.
You could do that, but that might be a harder problem. You could probably create 2 machine learning algorithms, one to detect a box around a single digit, and then pass that to this model.
I see.
Do you see what I'm saying? And so you could do both. Because the most important part of data science is the science bit, where science is literally guess and check, but more rigorous, and we write stuff down.
I see. So the smart person would do the thing you said. Let's make this problem simpler. Let's take apart these 2 numbers, but then still deal with them as a single digit.
Maybe. I mean, I guess it depends on how people write numbers the same way, but let's just say it was handwriting recognition and the script was Russian.
Yeah.
Russian script is notoriously difficult to understand because everything kind of runs together. Maybe it wouldn't work that way. Maybe it's better to learn words, or maybe it's better to learn something else.
So it depends.
It depends, yeah. I'm never going to say it. So now this thing, I think, should be about, it's 1 more epoch, but you can see that it's getting 98% accuracy on the test data, because what happens is once we train on the data, we leave some other data out, and we see how well are you doing on this data that you've never seen,
exactly.
And that's the test data set. The other thing that's important is this loss function. This loss function basically is measuring how bad are we at it. And if the answer is 0, then we're 0 bad at it, which is great. If the answer is 50 million, we're 50 million bad about it, which is not so great. So as this thing loops down, what I'm looking for is increased accuracy, decreased loss. And loss just measures the difference between what we predict and what the right answer is.
Right. And so it sounds like there's kind of a relationship between those 2 numbers, but not exactly, because they're determined in 2 very different ways.
Yes. So the difference between the loss function and the accuracy is the accuracy, think of it as an absolute. Either the max index is either right or it's wrong. But for the loss function, it's going to be filling numbers out through the whole thing. And so when you subtract those continuous values, you're going to get a continuous answer, right? And for accuracy, it's either right or wrong, and you count that up.
I see.
Yeah. So this should be the last epoch, and what it's going to do is it's going to output that model.ONNX. So I better close this before I get a file open error.
Because then we have to start again.
Yeah, because then we have to start all over again. But like I said, it's pretty simple. Just think of this as a AI. You have to pick a model shape a priori. Then you pick some hyperparameters like the learning rate, and the learning rate is how fast do we learn this stuff. And another batch size and epochs, how many, and then you run it, and then it's either good or it's not. And if it's not good, you switch to a different model, or you switch hyperparameters or whatever.
Right, and I assume as you get into this, you either have to teach yourself those sorts of things so that you can direct your efforts, or it would help to have someone like Seth on your team,
maybe,
so that they could give you tips on what to do next?
So I am like the school-trained data science, and I've been making demoware for the most of my career. So we have other people on our team like Francesca Lazzari, who bona fide data scientists. They have a good horse sense about these things, right? Like they look at the learning rate and they look at the loss function, and if the loss function goes up, they'll automatically be like, the learning rate is too high.
So he's like a model whisperer.
Yeah, she is.
She's
pretty amazing. Or for example, like if your batch size is too large, it might not be working. Or for example, if you notice that it's not learning very fast, or like the difference between your training error and your test error is either too high or too low, you start to get a sense for what is actually going on. And once you know what it's optimizing, it makes a little bit more sense. But once you pick the model function, once you pick the right optimization method, once you pick the right hyperparameters, then the output is this ONNX file.
Right. So how do we use it?
That's a great question. So let me describe what ONNX actually is. Notice it got about 98.4%.
So are you happy with that as the?
No, there's some that do better. But I wrote this myself the other day, and so maybe I should like tweak it a little bit better. Right?
But what would make you happy would be like, we're done. This is good.
I think 100% accuracy feels wrong to me because it overlearned.
Yeah.
And it's something called overfitting. But if it got 99.9, I'd be okay with that.
Yeah.
So basically what we need to do now is we have this ONNX file that it just built. And what I need to do is I need to use it inside of a .NET application. Now let me explain what ONNX is. ONNX is the Open Neural Network Exchange format. Think of it as like the PDF for neural networks. So anyone can build anything anywhere, but if you can export your model, which is like those pipes with all the gauges pre-turned correctly, then you can use that almost anywhere. And we happen to have something called the ONNX Runtime that you can literally just pull in with the NuGet package. Just pull in the NuGet package for the ONNX Runtime. And I don't know where it is. Where it's system, it's like system dot runtime. There it is. There it is. The ONNX Runtime.
Yeah, that makes more sense.
And the primitives for that.
And lots of pixelation.
And all this. Oh, that's pretty. You like that?
Yeah.
I want everyone to see. I could zoom in even more for you.
No, that's good.
So there's two things that happen. Once we do that, we basically need to load the file. And wow, this feels like it's really small. So let me.
You just need to do this guy down here.
And biggen this to like 200. Okay.
Much better.
So what I'm going to do is the first thing is I'm going to load the file, right? Because it's an ONNX file. And I'm using WinForms just because I want everyone to know. Like this is just regular .NET. I think it's a .NET Core thing. And so the first thing I do is I create this inference session, right? And what I do is I keep that globally as a global variable inside of the class because like I might do more than one inference and I don't want to have to load this file up. And I know it's not very big. How big is it? Let's see here. It's like 99K.
So it's not going to kill you.
It's not going to kill you, but there are some models that are like 250 megs.
Okay. So it varies a lot.
Yeah, it depends. This is a really small model with not a lot of numbers, right? And so basically, once I load it up, I'm saying, well, I'm running this.
Can we just pause for a moment? And the reason is because your domain is small.
Yes.
Because you said the images were like 28 by 28 or something?
28 by 28 pixels, yeah.
Yeah, so that's already very small.
Yes.
And it's basically black and white.
No, it is black and white. It's grayscale, yeah.
Yeah. So just the amount of possibilities that can exist in that space is very small.
Right.
As opposed to a model that is capable of like reading feature-length movies.
Yes.
And giving you some sort of feedback on it.
Yeah. So for example, if you want it to look at a feature-length movie and predict whether there was a dog in it, that's difficult, right? Because now, remember, we just have a single vector that's 784 that represents the pixels itself. But now we have a 4D tensor for the height, width, length, color, right? So RGB, right? Or maybe even alpha channel, and finally time. So it's a 5D huge thing, and we got to pass this in. And generally, the more stuff you pass in, like you got to have a better predictive model, and these things tend to get pretty deep.
Yeah, so that would be bigger.
Yeah, that would be a much bigger, or an even simpler one would be like if looking at a picture and predicting whether it's a dog or a cat. For example, the picture is like, let's just say it's 500 by 500 pixels picture, right? You have 500 by 500 by 3, which is the pixel depending on the channel. Sometimes the channel goes in the front, so it's 3 by 500 by 500. That one goes into the network, and then it does all the multiplication. But you have to, a priori, and this is the bit that's cool, is you have to actually pick the model function, right? I picked this one. For this one, it's pretty small. Other ones are much bigger. And this is, again, we're speaking strictly about computer vision. Like NLP, natural language processing, uses networks which are considerably different but similar.
Okay.
Yeah. Okay, so once it's, did I answer your question?
Yes.
All right, so this is basically coming from you can see the Inference Session comes from the ONNX Runtime, and I load it up from the file, and that's it. And then what I do now is when I want to actually do the prediction, I have to get the picture. So what I'm going to do is I think I set some strategically set up breakpoints, and I'm going to run this. And the first thing I'm going to do, by the way, this is all on GitHub. We'll put a link below. You can totally you can use this. So I'm going to do a load model, and I am going to get this. This is the outputs.
Right. This is the thing that you
we
just
literally
generated.
just built it. So I'm going to hit this, and see it's using a local model here. And now I'm just going to, with my finger, draw the number 3.
Okay, and it's not, I mean, to be honest, it's not even a very well-written 3.
Yes, and I knew you were going to bring that up because I did that on purpose, right? And it might not do a good job, because maybe it didn't have enough digits, or maybe it never saw something like this, and maybe it didn't reach that space of the optimization. So I'm going to hit recognize, and the first thing we need to do is we need to convert that into a 28 by 28 pixel image.
Right, because that's all the model.
Because that's all it knows.
Yeah, exactly.
And so notice that I'm doing that. I'm using I think I used a canvas, ink canvas on a WinForms application, you know, and inside of I don't know what they call them, where they can put XAML inside of WinForms, but I did that. You can see I resize it to the appropriate size, which is 28 by 28. And then I create a single float array that's size by size. And then for each one of them, I take the average of all of the colors and subtract 255.
Makes sense, because the bitmap is color-oriented.
Yeah.
Yeah.
And this one is not.
This one is not.
And now I return this thing. So if I go to run to cursor here, you'll see that this is basically just a vector or an array of floats.
Yeah, it's just an array.
It's just an array.
Yeah.
All right. So now let's go to the other one. Let's see if I put a breakpoint there, because that's yes, I did. So I'll hit F5. Notice that it gets the digit in there, which is a float array. And now we're using standard .NET types. The tensor of T is a data type that was introduced probably maybe a year ago.
I think it was in .NET Core 2.1.
So tensor of T is a way of nicely indexing into memory as if it was an array, but it holds it in contiguous memories. I'm not sure of the internals, but I think it uses span of T and memory of T in order to make sure you can do that. In fact, you can use tensors and marshal memory into C applications.
Yeah, which is great.
Which is great, and then when they write, the C program writes into it, because you're using memory of T, it's writing directly into the memory space of the .NET application.
Right, so no copying.
Yeah, which is really good. So for example, if I wanted to write my own linear algebra package, I could literally call into Kubla LawPack, for example, that's written all in Fortran and C, and it will write into that memory for me. And so now we can build some really efficient algorithms that use all the stuff that we use before. So that's one of the cool things that I like about this. But basically, the reason why we use tensor of T is because that's what the ONNX runtime expects for the input.
Right.
The next thing I'm going to do is I normalize the image, because that's how it's trained. Now, you're probably wondering what that means. Let me run the cursor. There you go. Basically, what happens is, instead of training on 0 to 255, I divide all the numbers by 255, so it becomes a number between 0 and 1.
Right.
That's how we trained it, so that's how we have to pass it in. Now, you're probably wondering, what is this bit? Well, this is to describe the input, and I'm creating it from this tensor. I'm creating a tensor from this named ONNX value. And you're like, well, where does that come from? Well, remember when I said we looked at this model, and there was an input that was named 0? That's the thing that's going in. Right? And I don't know why it called it 0. When it exported, it just did that.
But it doesn't really matter.
Doesn't matter, but that's the name of it. So if you don't know what it is, you're like, oh shoot, what is it? You can just look at using this, or you can go into the session itself. Did I right click in here? Let me see. Let's go to quick watch here, and you can see that in the session we have this input data named 0.
Yeah.
And so that's how I knew. That's the one to use. Okay, so now that we've done that, we do the named ONNX value. Then I always put this in a try block just in case something goes horribly wrong. I do a session run. Go ahead.
Yeah, so here's a good example. You were talking about, this is just running on .NET Framework.
Yeah.
Just I can tell from those version numbers.
I am going to circle this so that everyone can see your phantom finger that they will not see on the screen.
Yes.
Rookie mistake.
Yeah, totally.
Okay, so now what I'm going to do is I'm going to do the prediction here. So I'll do F10. Right, I do a run and I just get the first answer out. And I go to tensor to array, and you can see that now it's basically a vector that has a bunch. Oh shoot! Let me just do a quick watch so it doesn't disappear here. So there we go. Quick watch. It's literally a vector of size 10. And that's going to tell us what number it thinks it is. Right, and we pick the max index. So what did it guess?
I'm guessing it's this guy right here.
Here, I will use.
Oh, sorry.
Rookie mistake again, dude.
Yeah.
Gosh, this one right here, right?
Yes, because the other numbers are very, very small.
Very small.
Even though they have a number before the decimal place, they're
minus 14.
Yeah, so
maybe you should fix that, like put like a little bar chart or something.
Something like that. So,
right.
So it's extremely confident that it is 3.
That's right. And what I do is when I return it, I basically return like that it's not an empty prediction and that the prediction is the max index. So array.index of. I'm being pretty fast and loose with this, but I just wanted to show. And then I select all of the scores and I make it a list because that's what it expected it. Now I don't have to do that. I could just return the array, but I had just set it up this way because this also will call into REST endpoints to do the same kind of inference. So I'll do F5, and you'll see that it thinks it's 3.
Right, and we have that those scores shown in a bit more of a human-friendly form.
Yes,
there.
right. That's right.
Now the 250 seconds, that was more about how long it took you to demo this.
Yeah. So let's do it again here. So we'll do recognize, and oh shoot.
Yeah. I think you'd have to turn off all the breakpoints.
Let's turn off all the breakpoints.
Just saying.
Just saying. So recognize, right?
Okay, now we're well under a second.
Well under a second.
Yeah, because that's like 7 1,000ths of a second.
Let's do an 8 here. Right.
Now do something like do a letter instead.
Not only that, let me just start to screw it up. Okay, so I'm going to do this, and then I'm going to do this, and then I'm going to like put like a line between here and see what happens. It still thinks it's an 8, but notice that there's uncertainty that starts to come in. Now what I'm going to do is I'm going to try to do this to try to make it like a 7 too and see what happens. Right? Do you see how now the probabilities start to go a little bit down?
Mm-hmm.
Right? Because it's becoming less and less confident about these things.
Yeah, it's interesting though that it's leaning more towards 3 than it is towards 7.
But here's the thing, like I want to be very clear about this. It's not thinking. It's basically when you pass those 784 numbers in, the weights that it picked to multiply by and then function over and then multiply a function over, that's what it's returning at the output. But it's not thinking. AI has no feelings. For all those that talk about like, is AI going to start thinking? No, I think people should start thinking. Yes. Because you might as well ascribe.
That would be a good idea.
You might as well ascribe like this kind of intelligence to a rock, and it would be the same thing.
Yeah.
Right, we're basically doing an optimization algorithm to come up with something that will spit something out. I notice that it's guessing 3 and I've screwed it up. I could fill the whole thing in and it will still guess something because again, it's just multiplying matrices. Oh look, it thinks that's a 2. And then there's times where it will get things wrong too. And that's because we trained it on specific digits, and if there's numbers the way that you write differently, it will not.
So this is interesting. This goes back to the not thinking part. This system doesn't really have a way of saying, I don't know. Like you or me, with our AI system, or just we can see that last thing that you said and said, well, I'm not prepared to say what number I think that is because this is gobbledygook. Whereas this one basically just says, I'm always going to do best effort. I will give you a statement of how accurate I think this is. But that is all I am capable of. I don't have this is gobbledygook
and I even hesitate to say like this is how accurate I think I am. Basically what I did is I forced a function at the endpoint that forced them to look like probabilities called a softmax. And so I'm basically forcing it to pretend to be confident with those numbers, right? And so it's not even like I could have just not done the softmax and just picked the max number, and you'll see that some numbers are higher, some numbers are positive, some numbers are negative, right? But in the end, like if you want to ascribe like the unsuredness, you would return a vector of 11 and give it examples of things it's not sure about.
Oh, I see.
And then it would return that.
Okay, but you didn't build that.
I didn't build that. And that's the thing. It cannot do anything you did not explicitly train it for with the right network, with generating the right weights.
Okay, makes sense.
All right, any questions about it? By the way, this is all available right now. PyTorch 1.0 will natively export the right ONNX format for you to use inside of .NET applications.
Right. Oh, so in this case, you use the ONNX Runtime directly. What about ML.NET? Can it also use these ONNX files?
So the thing about ML.NET is it's used for training.
Okay.
Remember, you got to separate the process. But you can also use ML.NET to do the inferencing as well. But in your brain, you should still separate the two processes. Training takes a long time and is very tedious. And what was the word you used that gymnasts used? The contortions?
Contortion.
There's a lot of contortions during the training
bit.
bit.
On purpose.
But when you are running the model, we call it inference, it's a separate thing. It's pretty fixed.
Okay.
Yeah.
So
with ML.NET, you can both train the model and do inferencing. ML.NET, as far as I know, does only what are called shallow models. It's not a bad thing. Shallow models work really well, like decision trees or logistic regressions. It does those kind of models. This, for ONNX in particular, is for neural networks.
I see. So kind of apples and oranges.
It could be. It could be like, yeah, like remember how the example was that you put down the pipes and turn the knobs? There's a fixed class of the style of pipes you can put down and where the knobs are.
I see.
For deep learning, they're neural networks that are stacked. For other ones, they're more shallow, but they get the job done too.
So just in closing, can you tell us a little bit of, are you working with Microsoft customers today who are using the sort of thing that you just showed?
Oh, absolutely. This exact example, no, because this came out at Connect.
Yes, but more like, are there industries where you're seeing this sort of thing being picked up?
Oh, absolutely. Like a lot of people are using AI. They mostly put it into production some other way, like they put a REST endpoint, but people are using it for fraud detection. People are using it for recommendation systems. There's a lot of stuff. Like, think of any algorithm that you've had to write where there's like a lot of if statements and for loops and you feel like you need to go home and take a shower because you just kind of guessed at what it would be.
Yeah.
Those are the kind of algorithms that really fit well with machine learning, because instead of you coming up with a series of steps to solve the problem, you give it examples of the right thing, like in this case, numbers and the actual digit pixels and the digit, and then it comes up with an algorithm.
Awesome.
All right, bud.
Okay, well, thanks for coming by. Yeah.
All right, bud, we'll see you next time.
Okay, this has been another episode of On.NET about machine learning with Seth Juarez. Thanks.